Hi guys, welcome to this short lesson on epithelial transport. This is pretty closely related to membrane transport, which is why I do it here. Epithelia are fairly important for the function, really, of most organ systems. Pretty much anything with a lumen has an epithelia that is responsible for transporting substances from one side of the epithelial layer to the other. So as you know by now, the epithelial layer is a single cell layer here. And you can find that layer in exocrine glands where you're generating something like sweat, and then you're sweating, and you're moving solution from the lumen of the gland into a duct and then out onto your skin. Absorptive organs like the GI tract, they're lined by epithelia, which are responsible for absorbing nutrients and such. Secretory organs like the kidney, the lungs, these are all organs that where a lot of transport takes place, or you need an epithelial lining around some sort of a lumen of some type. So they are responsible for moving solutes from one organ or tissue to another, and again, specifically, most often from a lumen to the lumen of an organ to the tissues, or from the tissues to the lumen. The first and major difference between the epithelial cells and most of the other cells in the body is that they have polarity. That is, they have a sidedness to them. Epithelia have an apical side, which faces the lumen. This is your figure. It's the same thing. Apical side up here, basolateral side down here, and down here on this upper graph. The basolateral side faces the tissues. It's usually surrounded by intracellular tissues, intracellular space. The apical side faces the lumen of whatever organ that you're talking about. If it's the GI tract, obviously it's the lumen of the GI tube. That polarity, that sidedness of the tissue layer is actually maintained by tight junctions, and that's these here. Tight junctions are cytoskeletal elements that hold these cellular membranes in apposition, and they generally are a barrier to the movement of substances from one side of the membrane to the other. They also form a barrier in the membrane, so proteins that you find in the apical membrane don't make it past the tight junction to the basolateral membrane, vice versa. The basolateral proteins are blocked from getting to the apical side by the tight junctions. So the tight junctions maintain this cell polarity. As I said, they restrict movement from one side of the layer to the other, and how much they restrict movement of substances varies. Sometimes you'll find tight junctions that aren't very tight at all, and they'll let almost anything through. And sometimes the duodenum is a good example of that. Sometimes you'll find really, really tight junctions, like in the colon and in some parts of the kidney, where it's tough to even get water across. That varies from tissue to tissue, and that's something that you should remember. The term tight doesn't mean impermeant, the substances that get through will vary from tissue to tissue. There are two kinds of transport that take place across an epithelial layer. One is pericellular transport. That's transport around the cells through the tight junctions. A lot of times you'll find water will move this way. In particular, the tight junctions tend to be more permeant to cations than anions, so sometimes you'll see sodium get through, things like that. They'll move between the cells. And then there is transcellular transport, which, as the name implies, means transport through the cell. Meaning that, for instance, if you have an amino acid here in the lumen of your organ, the amino acid will be transported into the cell, in this case through a sodium amino acid co-transporter, and then out to the basolateral membrane, in this case through a transporter in the basolateral membrane here. So this is transcellular because the amino acid is finding its way through the cell, not around the cell. Okay? This is the best way to attain directed transport of specific substance. Transcellularly is the way you'll often find that to be the case. The transport through the tight junctions tends to be less specific. So you have absorption, which can take place across a epithelial layer. Absorption means transport from the lumen, the apical side, to the basolateral side into the tissues. This is absorption into the body. Secretion means transport in the other direction. That is transport from the body, the intracellular fluid, to the lumen, to the apical side, the lumen of your organ. This takes place most notably in the kidney for some substances, where you'll actually want to move things into the lumen of the kidney tubules in order to urinate a lot of that substance. Okay, that's trouble enough for another day. We'll learn about that in the vital fluids block. For now, just know secretion from the body, from the intracellular fluid to the lumen, through the apical side of the epithelia, and absorption from the lumen, the apical side, to the basolateral side, the intracellular fluid. Okay? So, it's very hard to make generalizations about epithelia because they vary from place to place, and it depends on what you're trying to transport where, which proteins you find. But most of the time, okay, you will find a sodium-potassium ATPase in the basolateral membrane. And this sodium-potassium ATPase, most of the time, what drives transport, usually by generating a sodium gradient. And I'm going to show you some examples of that in a moment. Okay? So, tough to make generalizations, but most of the time, when you're looking at an epithelia, most of the time you can start by figuring there is a sodium-potassium ATPase in that basolateral membrane. All right, so in order to see how epithelia work, I have a few examples I want to run you through here. Now, you're not responsible for the specifics of this transport. For instance, this is glucose transport. You can learn about glucose transport later. What I want you to hold on to are the general concepts of how paracellular transport works, how transcellular transport works, and what some of the, for lack of a better term, rules are for the transport, how things have to operate in general. So, having said that, the glucose transport across an epithelial layer is a pretty good example of how typical transport across an epithelial layer starts. So, as I said, ordinarily you can start by figuring, okay, there's a sodium-potassium ATPase in that basolateral membrane. And you'll be right 99% of the time. Okay, there are very few exceptions to that rule. So this is here, and it's generating a sodium gradient across the membrane. It's transporting sodium out and potassium in, so you're going to have high sodium here, and more importantly, low sodium in the cell when that transporter is operating. So we have low intracellular sodium, okay? So because we have low intracellular sodium, we have a gradient for sodium from the luminal side across the apical membrane to the intracellular side, okay? Sodium, as you know, will want to move from high concentration to low concentration, and as you know now, you can have secondary active transporters which use that gradient where sodium moves from high to low to drive other substances up their gradient. In this case, it's glucose, which is being picked up in the lumen and driven into the cell up its gradient. So you use the energy in the sodium gradient, you use the fact that sodium wants to come in and you make this transporter bind glucose in order for sodium to be allowed to come in, and therefore glucose is dragged in right along with it up its gradient, and you have glucose transport from the luminal side to the cell. So now we have glucose in the cell, we have sodium in the cell that came across here, and now those are transported across the basolateral membrane. In this case, the glucose is transported through a uniporter. I have high glucose in the cell because I've driven glucose in, and high glucose here, low glucose here. Glucose goes down its concentration gradient through this transporter, the glucose transporter in the basolateral membrane, and now my glucose is in the intracellular space. Sodium is transported out through the sodium-potassium ATPase, so it makes its way out of the cell, and we've transported glucose and 1 sodium across the cell, okay? And this is a good example of transcellular transport, okay? Note that when you transport particles from the lumen to the intracellular space, you've increased the osmolarity in the intracellular space. And as you know, we can't have water gradients across cells. This membrane can't stand water gradients, this membrane can't stand water gradients. If there's an osmotic difference between here and here, water is going to move to try to correct that difference. And in this case, water moves through the tight junctions from the lumen to the intracellular space, right along with our particles to keep our osmolarity constant, okay? So water is transported across this epithelial layer along with the glucose and the sodium, okay? Otherwise you'll have the osmolarity will build here, you'll have an osmotic difference across the epithelial layer. That can't happen, okay? All right. Also note these chloride channels here and here. If I move a sodium across this membrane, that's moving 1 positive charge from here to here, okay? And if I move a positive charge, I have to move a negative charge with it in order to maintain electron neutrality, okay? So that's a very good general rule. That's something that always happens when you have transport across an epithelial layer. You have to maintain electron neutrality. That is, if you're going to move a positive charge from here to here, you have to do one of 2 things. You have to move a negative charge from here to here, and that's what happened here. Chloride came in with the sodium and it left with the sodium. Or you have to move a positive charge in the opposite direction. That is, another ion, another positively charged ion, has to move from here to here in order to maintain electron neutrality, okay? So that is something that always happens in these epithelial transport systems. So a couple general things to keep in mind. You're moving water when you move particles, and you have to maintain an electron neutrality when you do this transport, all right? Let's take a look at sodium transport. In this case, it's sodium reabsorption. For instance, you might find this someplace like the kidney, okay? So once again, we start with a sodium-potassium ATPase in the basolateral membrane, okay? Most of the time that's there. And that decreases the sodium inside the cell. So we have low sodium here, and here I have a sodium channel in the apical membrane, okay? This is an amiloride-sensitive sodium channel. It is usually open, okay? And so when I have low sodium here and I have sodium here in the lumen, sodium will go down its concentration gradient from the luminal side into the cell, just like so, okay? Sodium moves in. Now, how does sodium get across the basolateral membrane? Easy. Through the sodium-potassium ATPase, okay? So sodium is moved from here to here, through this channel into the cell, and out through the basolateral membrane, transcellular transport, okay? This channel in the kidney is actually controlled by aldosterone, which will actually increase the number of channels. So aldosterone will increase sodium reabsorption back into the body from the kidney tubules, and so you'll retain sodium. That's a fairly important regulatory mechanism that we'll worry about more in vital fluids. Not too worried that you know the details here, but do be aware of how this works with the channel and the active transporter in the basolateral membrane, specifically to the sodium-potassium ATPase, okay? Also be aware that if I move a sodium, I'm moving a particle, water is going to move right along with that because we don't want to build an osmotic gradient from the lumen to the intracellular space. So water moves through the tight junctions, paracellular transport, okay, in order to maintain the osmolarity constant, okay? And then finally, as with the glucose transporter, note the presence of the chloride channels. Chloride came in with the sodium and left with the sodium. That maintained electroneutrality. We brought across one anion along with our cation, one negative charge along with our positive charge. And that, of course, contributes to the osmolarity as well, which is even more reason to move water, because we have another particle with chloride here. Okay? Okay, let's do one more of these. This is an example of chloride secretion. So I was doing glucose absorption and sodium absorption, or reabsorption, depending on the tissue and the situation. In this case, we're moving chloride, but we're moving it from the basolateral side to the luminal side. So this is an example of secretion of chloride. Okay? Note the sodium-potassium ATPase, maintaining our sodium gradient, specifically maintaining a low intracellular sodium. And as usual, that's what's going to drive this transport process. In this case, the transporter involved is the sodium-potassium 2-chloride cotransporter. It's in the basolateral membrane, and it transports sodium from high concentration to low concentration. Okay? So this is driving our transport. The sodium gradient, the sodium wants to move down its gradient from high to low. And so with the sodium, we drag a potassium and 2 chlorides along with it. And they go up their concentration gradient from low to high. Okay? So we're building potassium and chloride here by using the sodium gradient as it flows down its gradient. Okay? So we've increased the chloride concentration in the cell. And now this chloride concentration, relatively high, we have a channel in the apical membrane. This is, some of you may recognize, the cystic fibrosis transmembrane conductance regulator. And as you might suspect, mutations in this channel cause cystic fibrosis. So it's a fairly important transport process that we will worry about a lot more in the vital gases block. Nevertheless, in normal chloride secretion, this is a normal protein, it's a normal channel, and chloride goes across the membrane from the cell into the lumen down its concentration gradient. Okay? So we have chloride being added to the lumen of our organ. Note that because we're moving chloride, sodium will follow. We're moving one negative charge, so we have to move a positive charge along with it, or we have to move another negative charge in this direction. In this case, sodium is going through with the chloride, and it's going paracellularly through the tight junction. And then you'll notice that because I've increased the number of particles here by transporting a chloride and a sodium, water will follow in order to maintain the osmolarity and prevent an osmotic gradient from building, which is something that you generally don't want. You maintain osmolarity across these epithelial layers most of the time, with the exception being some regions of the kidney. All right. All right, that's all I've got. Those are 3 good examples of how this works. We'll work our way through more. We have a computer workshop that is related to this. You'll do the osmolarity and cell transport computer program, and then you'll do an epithelial transport computer program in our computer workshop. Again, not mandatory. I don't like requiring students to do things, but I do strongly encourage you to come to that workshop. I believe it can help, and it's an excellent opportunity for you to ask me questions about this material as well. Having said that, after the workshop is over, I will post these programs so that you can download them and run through them at home and study them if you wish. A more convenient way to use them is to log in through myapps.rush.edu, and log into your computer desktop here. They are all on your computer desktop here, okay? And you can do them that way as well, but I strongly encourage you to come to the computer workshop. Take advantage of the fact that I'm there. I think Dr. Morgan will be there. He's another physiologist that you'll be becoming familiar with. Ask us questions and make sure you understand the problems as you go through it. Also, you'll notice that this lesson wasn't particularly long. It's one video, but there were a lot of pages in the lesson notes, and the reason is because at the end of this lesson I included frequently asked questions, a good sample of questions I've gotten from other students over this material before, and I've included some old exam questions which will be good examples of some of the difficulty that you can expect from me on the block exam for the HDHR exam and anywhere else where you'll be tested on this, okay? This is at the end of the lesson notes. Be sure and study those for the exams and any formative quizzes that this material may be on. All right? That's all I've got. Thank you for your time, and I'll see you guys in the workshop and later on in the rooms.